So tonight we're going to be thinking about power. So energy can be put into a system. By converting fuel, which is chemical energy, into a driving force, which is mechanical energy. The work done by the engine is given by the force times the displacement, which we've already seen. So Fs. Now power is defined as the rate of doing work. So the average power generated by an engine is given by, so we think about the average power because there'll be fluctuations in an engine. The average power is the work done by the engine over the time taken. So we think, so work done is F force times displacement and over the time taken T. It always takes the same amount of work to make a car speed up from 0. So we've got a car and it's going from 0 kilometers per second to 100 kilometers per second. It's the same amount of work done to go from 0 to 100 kilometers per second, but a more powerful engine that's regardless of the engine. But a more powerful engine gets there sooner. Now, if you imagine a very small time interval, so over a small time interval, actually I'll do this on a separate page. So we've got a small time interval, which we're going to call ds. The driving force, oops, what I'm writing there, F is constant, and the rate of doing work is given by the power, which is the rate of which work is done, is the force times ds by dt. So you've got this tiny, it's going to be a t. the tiny time interval. So it's going to go over this tiny little displacement in this very small time interval. As dt gets smaller, as ds by dt gets smaller, it tends towards ds by dt. So what we can then say is the power is the force times ds by dt. Now we know that ds by dt is the velocity, so the power can also be written as the force, the driving force, times the velocity. And this is when f is constant. Now power is measured in joules per second, but we more commonly call this watts. Power is measured in watts with the symbol W. Now, when we're talking about engines, the power is usually quite high, so we often will use units of 1,000 watts. So we measure it in kilowatts. Power is a scalar. However, if you notice, both force and displacement and velocity are vectors. So although power is a scalar, it's actually given by the product of two vectors. But this isn't a problem for us because we're only going to be considering motion in one direction. So we can just think of power as force times speed. If it was different, we'd have to be looking at different components in different directions. So let's look at some examples. A car of mass 1,500 kilograms is being driven along a road. It's a level road, so it's one direction. It accelerates from 0 to 100 kilometers per hour in 10 seconds. Air resistance and friction can be ignored. Find the average power generated. So we've got 100 kilometers per hour. Now we want to change this into meters per second, and that's 27.8 meters per second. That's always something to look out for, and something to just make sure you're comfortable in doing, is how to convert between kilometers per second, and also convert back from kilometers per second to from meters per second back to kilometers per hour. Work done. So the increase in kinetic energy is going to be the same as the work done by the engine, and that's due to the work energy principle. So our work done is going to be the kinetic energy, the change in kinetic energy, which is a half m v squared minus u squared. So it's a half times 1,500 times, now the velocity at the end is 100 squared, and that's going to be 0, so we don't need to worry about that. Oh no, it's not 100 squared because that's a kilometre. I've just been talking about, is 27.8 squared, and the initial velocity was 0. So our work done, which is the same as our change in kinetic energy, is 578,704 joules. So our average power is going to be the work done divided by the time taken, which is 578,704 over the time taken, which is 10. So that's going to give us 57,870.4 watts. And we'll put this into kilowatts, so it's 57.9 kilowatts. Now, for a given power, the driving force will be greater at lower speeds. So for a given power, the driving force will be greater at lower speeds and smaller at higher speeds. You can see that when we look at power is the force, the driving force times the velocity. So if we think what our force is going to be power over velocity. So if the velocity is smaller, the driving force will be higher, and if the velocity is higher, the driving force will be smaller if the power is remaining constant. For example, a car pulling off from stationary under maximum power, so we've got our car and it pulls off from stationary, is at maximum power. It has a low speed, so the speed is going to be small, but the driving force high. So it can move. So it can move off more quick. Well, it can accelerate more quickly. Therefore, it can accelerate more quickly. As the speed increases, the driving force will decrease, and then at some point there'll be no resultant driving force, and then the acceleration will be 0 and it'll go at a constant velocity. If the maximum power is maintained, acceleration normally will become 0, and the forces will then balance out. We can use maximum power output of an engine to find the maximum speed that it can generate. At the maximum speed, acceleration is 0, and hence the resultant force is 0. So the driving force will be balanced out by other forces on the car. So let's look at example of this. A car of mass 1500 kilograms has an engine that's maximum power output is 200 kilowatts. The resistance to motion is typically 5,000 newtons. Find the maximum speed the car can achieve. So like with so many of these issues, we draw a force diagram. So here's our car. Its weight is down here. R's here. The resistance is in this direction. It's 5,000 newtons. The weight is going to be 1,500 times 10, so it's going to be 15,000. And we have our driving force. And that'll be F. So the resultant force will be the driving force minus the resistance. At maximum speed, there's acceleration equals 0 because of Newton's second law, so therefore the resultant will equal 0 newtons. Therefore the driving force must equal 5,000 newtons. So we know that power is the driving force F times the speed, and we know the and so the driving force is going to be let's put our numbers in first. So we've got our power as 200, but it's 200 kilowatts, so we'll need to multiply it by 1,000. F is, what's what we've got up here is 5,000, and V is what we want. So V must be 200,000 over 5,000, and that will give us 40 meters per second. As you can see here, we haven't actually used the mass of the car. So the maximum speed is the same for any engine that has this maximum power and this resistance to the motion. Let's do another one. A car of mass 1,500 kilograms again has an engine with maximum power of 200 kilowatts again. The resistance to motion is again 5,000 newtons. Find the instantaneous acceleration of the car when the engine is at maximum power and the car is travelling at 20 meters per second. So again, we do our Reforge diagram. So we've got our weight down here, We've got R. We've got our 5,000 newtons of resistance, and we've got the driving force. And we'll call that F. So we know power is the driving force times the speed. And we've got our power here of 200,000 watts, and we don't know our driving force, and the speed is 20. So F is going to be 10,000 newtons. Now the resultant force, which is actually the one that will be causing our acceleration, is the driving force minus the resistance. 10,000 minus 5,000, and that'll be 5,000. So because of Newton's second, the force is F equals ma. So we've got our 5,000 newtons. Our mass is 1,500 times 8. So that gives us an acceleration of 3.33 meters per second. And we'll do one more problem. A car of mass, again 1,500, and again the engine, the maximum power of the engine is 200 kilowatts. Again, the resistance to motion is 5,000 newtons, and we want to find the instantaneous acceleration when the car is travelling at 20 meters per second up a hill that is the inverse sine 0.28 to the horizontal. So we've got theta here, and we've got our car here. There's some driving force. We have 5,000 newtons of resistance. We've got the weight, which is 15,000, and we've got R, and we know that the sine of theta is 0.28. Now there is going to be a component of weight, oh dear, down the slope, and that will be equal to the weight of the car times sine theta, which will be 4,200 newtons. Now the power that we know is the driving force. We'll put a little d there for the driving force, times the speed. So the driving force is the power 200,000 over the velocity, which is 20, which is 10 8,000 newtons. Now the resultant is going to be, so we've got the driving force up the slope, but coming down the slope we've got our frictional forces, the forces that are resistant to the motion, minus the weight, the component of weight. Oh, there's only 1 0. There's 2 zeros, not 3. There we go. And that will give us 800 newtons. Then using Newton's second, we've got our 800 newtons. Our mass is 1500 times our acceleration a. So a will be 0.533 meters per second. So I hope that makes sense.